you an overview of galaxies, and today I would like to talk about radio astronomy. Yesterday we had a bit of a problem with the time at the end. This is why I inserted some of the slides which were missing yesterday into my talk today. So, is the voice clear? Can you hear me?
Yeah, we hear you very well.
Okay, excellent. Okay, so let's start. What is radio astronomy? Radio astronomy is observation of electromagnetic waves from the universe. As you know, electromagnetic waves can be sorted according to wavelength. This is the upper part of this slide. So it starts in the kilometer range, which are the very long radio waves, then the meter waves and centimeter waves, which are still called radio waves, then the millimeter waves, sub-millimeter infrared, and then this small yellow part is what we call light, and at shorter wavelength, ultraviolet, X-rays, and gamma rays. And the lower panel shows the absorption of the atmosphere. So the absorption is in the very long wavelength part by the ionosphere of the Earth. So beyond wavelength of 10 to 30 meters. So this is the left part. The ionosphere does not allow radio waves to go to the Earth's surface. Then in the infrared, there's some absorption by the molecules in the atmosphere, lower atmosphere of the Earth. This is the lower mountain in this lower panel. And then in the ultraviolet and X-rays, we have very strong absorption by the ionosphere. And this is this big mountain. So on the right scale, you can see the average absorption in altitude above the sea level. So you can see that there are two windows. There's this yellow window, which is the optical window, where astronomy has taken place over thousands of years. And then to the left, we have the radio window. That means you don't need any satellite or airplanes or rockets. You can do astronomy from ground. And as you can see, the radio window is much, much larger than the optical window. Okay, so just see that the image is not yet visible on your screen. Is that true? So it's still the first image? Okay, I will try to go back and forth. Do you see the second slide?
Not yet.
Oh, there's something. Okay, I have to start it again. Sorry for that.
Yeah, we see.
Okay, now the second slide. So sorry, I have to stop this again. So the upper panel shows the different wavelength ranges of the electromagnetic waves, and the lower one is the absorption. And again, just very brief, there are two windows. There's this yellow window in the middle, which is the optical window, and then the radio window is to the left. And the radio window means you can observe from the ground, and the radio window is much, much wider than the optical window. So in principle, radio astronomy is very powerful. It can see radio waves from the cosmos, from the universe, from a few millimeter wavelength up to a few tens of meters of wavelength, and the telescopes which are run by our institute are shown in the middle, which is the Effelsberg telescope for the longer wavelength, and the millimeter telescope for the millimeter wavelength, and the Apex telescope for the sub-millimeter wavelength. But unfortunately, there's a problem. Next slide shows that, just wait a second until it arrives, right. Of course, as you know, radio waves are very popular for commercial purposes. So radio waves are used for mobile phones, radio waves are used for transmission of TV signals, of radio signals. It's used for radar. So radio waves are extremely popular among various applicants. That is why radio waves are very precious, and they are expensive. And this is why the radio wavelength range has been split into blocks, and these blocks via international convention are assigned to various users. I don't explain the detail here, just want to show you this is the official allocation of radio frequency bands to various users. These are private users, these are military users, these are commercial users, and only very small parts are kept free for radio astronomy. So on this picture, which the upper one shows the range around 1 meter, the middle one around 10 centimeters, and the lower one around 1 centimeter, only the purple areas, the dark purple areas, these are the ones which are assigned to radio astronomy. So although the radio window is very wide and we could observe radio waves from the universe over a wide frequency range or wavelength range, in fact we can do it only in very small bands because the rest is used by commercial emitters, and that means we do not have the chance to see radio waves from the universe. So we are fighting for this, and as you know, assigning radio frequencies is also expensive, so any TV station, mobile phone station have to pay for that. We cannot pay, so we have to send our lobbyists to the international conferences and just raise our voices and say we need this frequency range, and we ask the international community to keep it free for us, but it's getting more and more difficult. Okay, this is a few final introductory remarks. Now a bit of history. Radio waves were discovered in Germany, and we are very proud that Heinrich Hertz in the 19th century discovered them in the city of Karlsruhe, and after that he got a professorship at the University of Bonn, so our university here, but unfortunately he only worked here for a few years before he died very young, with the age of 37. And but still, Heinrich Hertz is the discoverer of radio waves with the transmission of energy via radio waves, and this is why the unit of frequency is still called Hertz, and Hertz is the frequency in units of 1/2, and you all know this is now called Hertz. So Hertz is 1 vibration per second. So kilohertz is 1,000, megahertz is 1,000,000, and gigahertz is 1,000,000,000 vibrations per second. So this is the convention. Sorry, was wrong. I have to go back here. Sorry for that. That was the wrong button. Okay. Wait until the picture arrives. The radio waves from the universe were discovered much later, in 1933, by the US engineer Carl Guth-Jansky, and so the top left panel shows the first radio telescope of the world, which is just a system of wires, and with this radio telescope he discovered that there is radio waves coming from the Milky Way, from a region called Sagittarius, and he had no idea what is going on in Sagittarius. As you may remember from my talk yesterday, now we know that Sagittarius hosts the center of our own Milky Way where we are living in, but Jansky and also all astronomers at that time did not know that, because radio astronomy was not developed, and optical astronomers had no idea where the center of our Milky Way is, because it is hidden behind dust clouds. So Jansky discovered that, but it was not appreciated because nobody really understood what the origin of that radio waves were. There were lots of speculations, but nobody had a very clear idea. And there are also people who were skeptical and thought maybe this is not a really good observation. And then a few years later, an amateur astronomer built the first radio dish telescope in 1937 already, Grote Reber, also in the United States. And this is looking like a really modern radio telescope, so you can imagine if this is an amateur astronomer, he must be extremely skilled. And he could confirm the observation of Jansky, and in his radio map shown to the right, he showed indeed that the radio waves are coming from the Milky Way. And that was a total surprise, because people thought maybe they are radio waves from the sun, maybe from planets, maybe from stars, but from the Milky Way, which is very far. As you know, the center of the Milky Way has a distance of 25,000 light years. That was nobody who could imagine where this emission was coming from. So that was again a mystery, and it took another 15 years until various people in Russia and Germany had the idea to explain where this emission is coming from. I will come back to that later. So then there was a time of World War II. World War II, of course, was not a period of intensive research, but still radio telescopes were needed, but not needed for astrophysics, but needed for detecting airplanes of the enemy, and especially in Germany, a lot of these radio telescopes were built and just looking for airplanes, and there are many hundreds of them, and some of them have been left over. So the left picture is one which has been placed during the war in Denmark, and the right one is one of the leftovers which has been transported to Cambridge in England and was used then after World War II as a test experiment for radio waves. So the first observations of radio waves started in the after World War II in the late 40s and early 50s. In Germany, the really first radio telescope was built in 1956, which is this telescope here. It's called the Stocker telescope, which is not very far from Bonn, was 25 meters diameter, which was for a short time the largest radio telescope in the world. But then already a year later, the British astronomers who were leading radio astronomy at that time, together with the Americans and the Australians, built this really huge telescope with 76 meters diameter in Jodrell Bank, which is near Manchester in northern England. This telescope is still working until today. It has been refurbished several times. So this is a classical radio telescope, a big parabolic dish. The parabolic dish is used to concentrate the radio waves, and then the radio waves are focused into a focal plane, and in the focal plane there's a receiver. I will show you a picture of the receiver later. The United States had then in 57 built an even larger telescope of 90 meters diameter shown to the left, but this was a very light construction. It was built only to be operated for a few years, and this is why there was no surprise that 26 years later this telescope crashed and it just fell down. Fortunately, nobody was hurt, but the largest telescope in the United States was not existing anymore, and as you can imagine, this was a very big catastrophe and bad news for the Americans, and normally they overcome that by building something better and something new, and this is indeed what happened. I'll show you that image later. But then in the late 60s, Germany also started to build up radio astronomy, especially here at the University of Bonn. Max-Planck Institute was founded for radio astronomy, and the 100-meter telescope Effelsberg was built, which is 100-meter diameter, which was the largest telescope, movable telescope in the world for many decades, and today it operates between about 1 gigahertz and 95 gigahertz in centimeters. This is going from a few millimeters to a few decimeter wavelength. And as you can see on this picture very nicely, there's the two focal cabins. The upper one is a primary focus cabin, and the lower one is the secondary focus cabin. You can collect radio waves in both foci, and next slide shows a view into the secondary focus cabin, and you can see different openings. These openings are the coverages of horns. The horns they can collect radio waves of different wavelengths. So the larger horns they collect larger wavelength, and the smaller one smaller wavelength. And to the right you see what happens below that in the secondary cabin. These big golden things are so-called horn antennas. The radio waves are just collected within these horns, then are transmitted to the end of the horn, and at the end of the horn there's a very small metal pin, and this metal pin is the antenna which collects radio waves and transfers the radio waves into an electric current, which can then be amplified. So all classical radio receivers look like that. All wavelengths need to have a different receiver, so you cannot tune between different wavelengths easily. Normally, if you change the wavelength, you have to change the receiver, and this is why in the secondary focus cabin we have many receivers which can be operated at the same time, and by just switching between the receivers you can switch wavelength. So as I mentioned before, the United States, of course, they lost their biggest telescope at that time in the 80s, but then they built a new one, which is now the largest fully steerable dish, which is slightly larger than the Effelsberg telescope, effectively 102 meters. It looks somewhat different. Effelsberg has 4 supporting legs. This has only 2. This is an offset mirror, which has some advantages, but also disadvantages. It's much heavier than the Effelsberg telescope, but it also operates very nicely since many years. Unfortunately, the funding situation in the United States has become extremely tight, and there's a discussion whether this telescope should be closed in future, and at the moment there is an action to save this telescope, because we need it. These telescopes of that size are really very important for radio astronomy. So the GBT is the largest steerable radio dish. We have also a largest radio dish which is not steerable, which has 305 meters, which is in the Caribbean, on Puerto Rico, belonging to the United States. This is fixed in a valley. It can operate between 3 centimeters and 1 meter wavelength, and changing the observing direction on sky is done by moving the primary focus, which is hanging in wires, and along these wires the primary focus cabin can be moved, and this is why you can observe around a certain area around the zenith, but of course it cannot observe the whole sky. So the largest telescope is in Russia. As you certainly will know, this is Ratan 600, almost 600 meters diameter. It's not a dish, it is a circle of segments of parabolic dishes. It's in the Zelentuskaya area in southern Russia, in the Caucasus area. It operates in the centimeter wavelength. But unfortunately, I have to say that the scientific outcome of this telescope is not really good. The reasons for that I don't know, and I will not comment on that. It was an attempt to build a large telescope of that kind, but the kind of construction obviously was not the optimum way. But it still is the largest radio telescope of the world. So going from the centimeter to the millimeter, the largest millimeter telescope is driven by Germany, France, and Spain. It is in the Sierra Nevada in southern Spain. It observed in the millimeter range. It's 30 meters diameter, and it can be the dish can be heated because you need enormous accuracy. I should mention that if you want to observe at a wavelength, shortest wavelength of 1 millimeter, then the accuracy of your mirror has to be at least 20 times better. So it has to be better than a tenth of a millimeter, and that can be achieved only if the mirror is temperature stabilized. So you need a heating, and that means you have a very high electricity bill. And if going to even lower frequencies, we have another telescope called APEX, Atacama Pathfinder Experiment, which is in Atacama Desert, because in the sub-millimeter range, below 1 millimeter, you're already fighting with the transparency of the atmosphere, and the insert to the left shows this color shows where there are further small windows. So the left big one is the remaining radio window, but then you can see 2 small peaks, which are windows where the atmosphere can transmit some radio emission, but only if you go to large heights from the ground. You cannot do that. You have to go to large heights, and this is why this telescope was built at 5,000 meters in Atacama. This is the second best place in the world for this sort of emissions, the best place in Antarctica, but logistics, as you know, in Antarctica is much more complicated. This is why we decided to build this telescope in the Atacama Desert. So far for the single dish telescopes, with all these radio telescopes, there is a problem that radio waves are long, and this is why the resolution of radio telescopes is relatively coarse. I will give you the formula in a minute. If you want to build a telescope which is significantly larger than 100 meters and it should be steerable, this will fail because just the gravitation is too strong on Earth. There's no material with which you can observe, with which you can construct a telescope which is much larger than 100 meters. So instead, you don't build one telescope, you build a series of telescopes, and one of the first ones of that kind was built in the Netherlands, in Westerbork. These are 14 telescopes which are built in a row of up to 6 kilometers. This is also still operating. The most advanced telescope of that kind is called the Very Large Array, VLA, in New Mexico in the United States. This is a Y-shaped telescope, 27 telescopes, and you can move them out into the desert up to wavelength of up to baselines of 25 kilometers. So each of these telescope can be transported with a big truck on a rail, and then you can move it out, and then you can even increase the resolution. So next slide shows the formula of resolution of radio telescopes. So this is just an approximate formula. The angular resolution of a radio telescope depends on the wavelength and on the diameter, so with any unit. So if you insert the diameter of the Effelsberg telescope of 100 meters and the wavelength of 3 centimeters, you will get a resolution of about 1 minute of arc, and this is almost exactly the same resolution as the naked eye in the optical. So although the Effelsberg telescope is much larger than your eye, the resolution is still the same because the radio waves are also much longer. So that means the radio telescope at Effelsberg sees the sky with the same resolution as you would see it with your eye, as you see it with your eye. So that means we can see in radio astronomy also structures on the moon, and the resolution would be similar as if you would look to the moon. Also on the sun, we would see sunspots also in the radio, but we can barely see them with this resolution. So this is the basic problem of radio astronomy. The resolution is very low. And this is why these interferometers have been invented, and the lower shows the example for the VLA. It can be extended to a baseline or a diameter of 25 kilometers, and then you really get resolutions of better than an arc-second. Optical telescopes reach about the same resolution. So with this VLA, we can reach similar resolution as optical telescopes can reach, and there are even possibilities to do this even better. Just to finish my part about the radio telescopes, there are plans to do more interferometers. There's a plan to build a big interferometer in the Atacama Desert called ALMA, Atacama Large Millimeter Array in Chile. This is a common project of the United States, Europe, and Japan, and this is under construction, and that will give a very high resolution, much better than an arc-second in the millimeter range. And finally, I want to mention that you can use this interferometric principle also by connecting telescopes all over the world. This is called a very large baseline interferometry, VLBI, and this allows to connect telescopes in different countries. Also, regularly observations are done between Europe, Russia, and the also China, and this allows to get resolutions which are much better than any optical telescope, even a space telescope can do. I will show you examples of these observations later. Okay, I think I will stop here for a minute, and then you have the chance to ask questions.
Is there any questions in schools? We haven't.
No questions?
No.
Okay, then I will. Okay, so now I have explained how radio telescopes look like and how they work. Now I have to show you some examples. What can we observe with radio telescopes? And I start with the most important discovery, I would say, of radio astronomy at all, which is the discovery of the cosmic microwave background. Microwave is a word similar to radio waves. It's just shortwave radio waves are called microwaves. And it was discovered that from a period about 300,000 years after the Big Bang, whatever that was, there is a period where there was a strong emission of waves. At that time, it was not radio waves; it was waves in the UV range. And sorry, I was mixed with my slides. And this original cosmic fireball, this original emission of energy in the whole universe, was then changed into radio waves because the universe is expanding. So in the beginning, this emission was very bright and was in the ultraviolet, but then during time until today, in the 13.7 billion age of the universe, this moved from the ultraviolet into the radio. And we can describe this as a temperature, as a black body temperature. And the black body temperature of this emission from the very early universe can now be described by a temperature of a black body of 3 Kelvin. And a 3 Kelvin black body, this is the lower part of this curve, is shown there. It can be detected only in the radio. And that means the whole sky is extremely bright in the radio. It's much brighter than anything else, but it's very hard to see because it's covering the whole sky. And to see this took a long time. People were not aware of this, and only if you have a telescope which is able to move below the horizon, you will realize that this emission is suddenly disappearing and the sky is bright. And that was done only in 1960, although radio waves were known already long before that. And these two engineers, Penzias and Wilson, discovered that with the antenna shown in the background, and they were awarded the Nobel Prize for Physics in 1978 for the discovery of the cosmic microwave background. And this is the strongest indication that there was a Big Bang, and no other alternative model of the evolution of the universe succeeded in explaining this cosmic microwave background. It has an enormous energy density. It's filling the whole universe, and this everybody is convinced must come from these early times of the universe. So the cosmic microwave background, I've already shown this picture yesterday, has been started in much more detail with various satellites, with the Kobe satellite and the Wisconsin Mapper satellite, and it showed that the cosmic microwave background is bright, but it's not homogeneous. It has fluctuations, and these fluctuations are the seeds for the formation of galaxies, as I have explained later. And this gave another Nobel Prize for Physics in 2006. So you can see that radio astronomers were really very successful in collecting Nobel Prizes because they discovered things nobody has ever imagined before. So cosmic microwave background is also very good to study the physical conditions in the early universe. I've also shown this already yesterday. These fluctuations are not smooth and not a turbulent spectrum. but they have certain amplitudes which are more frequent, and on a degree of on a scale of 1 degree, there is a peak, and that means there are obviously sound waves traveling at that time, and that helps us to understand the early universe, and that allowed us to measure the age of the universe, because with a sound wave you have a scale of the sound speed and the sound travel length, and knowing the roughly the size of these objects in real units like kilometers, then you can measure the distance to these objects. If you have the distance, then you know the age, and this allowed the astronomers to determine the age of the universe, and now we know that the age of the universe is 13.7 billion years, and the error bar is relatively small, so this is less than 0.1 billion years. So the age of the universe could be very precisely measured with help of these observations here. Okay, that's already something I've explained yesterday. Now coming to other sources of radio waves. So what has been speculated already in the very early times is that hot gas should emit radio waves. So what is hot gas? Hot gas are, for instance, stars. So our own sun, optical picture shown in the lower left, should emit radio waves. And the right is indeed a radio image of the sun. Indeed, it emits radio waves, and the process is so-called thermal radiation. So if in a hot gas an electron moves and is entering the electric field of a proton, then the electron the path of the electron is bent, and that means an electromagnetic wave is transmitted, and this transmission is called thermal emission. And as you can see, sunspots in radio are not dark, but they are bright. So the colors in the lower right panel are just according to the intensity. So red means bright and yellow means weak. So sunspots are bright. This is not the same day, it's just a different day. I could not find the same optical image of the same day. So radio sunspots are bright, and that means sunspots are hotter than the surroundings, which is a surprise, because we know that on the surface of the sun, sunspots are cooler. So that cannot be the sunspots themselves, which we are observing in radio. It must be something else. And what we are seeing here is a corona, is the layer of the sun above the sunspots, and indeed the corona above the sunspots is brighter than the surroundings. So other hot gas objects on sky are gas nebula. I've explained that yesterday. So red nebula on sky in galaxies are heated up by stars, and these stars produce hot gas, and the hot gas indeed emits radio waves. So this is nothing really exciting and not surprising, and this is why I move on to things which have been discovered, which were not expected. So astronomers and scientists are always excited if they find something they did not expect and they did not predict. So this was predicted, but the discovery was still a very important step of radio astronomy. Neutral hydrogen, so cold hydrogen, the electrons are bound, they are orbiting around the proton, but they can change their state, their angular momentum. It can be parallel or anti-parallel with respect to the angular momentum of the proton. And if they move from parallel to anti-parallel, energy is released, and this energy has a certain quantum, and the quantum energy corresponds to a wavelength of 21.1 centimeter. So if you observe an emission of 21.1 centimeter, then you know that you have neutral hydrogen at this point on sky. And this can be applied, for instance, to galaxies. And again, my special friend Andromeda galaxy, this is the optical image, and the next one is the map of the neutral hydrogen observed in this line. This has been done already some time ago, and this is showing that galaxies are much larger than what you see in the optical. The neutral hydrogen is still lying around, and the neutral hydrogen is a potential building material to build further stars in future. And another thing is very important. This is the Doppler effect. The Doppler effect tells us that the frequency or wavelength of the emission can be changed if the object is moving away from us or is moving towards us. If the object is moving towards us, the frequency is enhanced. If the object is moving away from us, the frequency is becoming lower, or the wavelength is becoming longer. So this is well known, and it can be applied to observation of H1, for instance, with the Andromeda galaxy. So you see on the upper part, the color now indicates as a red shift. That means the object is moving with about 100 kilometers per second. On the other side, it is blue shifted. It is 600 kilometers per second. The average of that is 300 minus 300 kilometers per second. This is the average velocity the Andromeda galaxy moves towards us. So now you can easily compute when the Andromeda galaxy will crash into the Milky Way. That takes some time. You don't be worried about that. But additionally to that, you see that the upper part is moving obviously slower than the lower part, and this is the rotation of the galaxy. So the difference is 500 kilometers between the upper and the lower part, and that means this galaxy is rotating. So without any sequence of images for which you would need millions of years to see the rotation immediately, with the Doppler effect, you can measure the velocities with just one single observation. So this is extremely powerful. So the Doppler effect applied to line emission can be used to measure velocities. And the accuracy is very high. You can measure velocities better than 1 kilometer per second. So, okay, I'll skip this one. Another advantage of radio waves is that we can look into dust clouds. So this is a typical dust cloud which is seen in the Milky Way. So dust cloud is dark. It means you don't see the light of the stars which are behind this. If you go from optical to infrared, you start to see a few stars, but these stars are really very red, so they are strongly changed their color, and you can imagine that it's not very easy to measure the properties of that dust cloud. So we don't know what is their density, we don't know what is their temperature, and for that we need radio waves, because in radio waves these dust clouds are not dark, they become bright, because in these dust clouds there are molecules, and molecules like carbon monoxide or formaldehyde, and these molecules emit radio waves. These emit radio waves at different wavelength, carbon monoxide at 2.6 millimeter, formaldehyde at 6 centimeter. So if these clouds are seen at this wavelength, again we know that these are molecules. So why is this important? So especially the formaldehyde H2CO is a quite complicated molecule, and this molecule can only exist if a dust cloud is very dense, and it's also very cold. Because dense means there's no UV radiation coming in from outside which could destroy the molecule, and cold means there's not a lot of thermal motion of these molecules, because also thermal motion can destroy them. So the pure fact that there is formaldehyde in this molecular cloud means that these gas clouds are dense and cold. So we can measure the density and the temperature of these clouds by measuring radio lines. And if you do that, you find that these molecular clouds, as we call them, because they are full of molecules, they cannot be stable. Their gravitation is too strong, and their pressure, because of the low temperature, is too low, so they will collapse. And that means we now understand how stars are formed. Stars are formed in cold and dense gas clouds because these are not stable and they can collapse. And so I also shown this yesterday already, a map of carbon monoxide of a galaxy like Andromeda shows you where they are dust clouds which are in the process of collapse. So all these dust clouds will soon form stars. So soon in astronomical timescales means that will take maybe a few more million years, but this is a relatively short time in astrophysical context. And also the Doppler effect can be applied again to the this yellow line, and this is another map of the rotation of Andromeda, similar as before, but now you can see this with much more detail. Again, velocity is changing by 500 kilometers from left to right, and you can see that individual clouds, they sometimes have different velocities. So there are clouds which have, so to say, the wrong color, and that means they have some proper motion. I should explain briefly why there's this change from left to right. This Doppler effect works only if the object is moving towards us or away from us, but in the middle of the galaxy, the rotation of the galaxy is in the sky plane. That means there's no velocity component towards us or away from us, and this is why this is yellow, and yellow minus 300 kilometers is just the velocity of the whole system towards us. So minus 300 is how Andromeda moves towards us as a whole, and then minus 300 plus or minus 200 kilometers per second, 2 or 300, this is the rotation of that galaxy, which can be studied in very much detail with help of this radio line. And I could talk another hour about radio lines, which is really extremely fascinating, but I will close this part of my talk just with showing you a spectacular result which has been found with the Effelsberg telescope. A molecule has been discovered at a distance of 11 billion light years. So this is at the edge of the universe, and this molecule is very well known. It's water vapor, it's H2O. And this has been discovered. This is this yellow line, marked yellow, in a very distant galaxy. This is not the galaxy itself, it's the galaxy core, and it's not even the core, it's a surrounding of a black hole within this galaxy. And it means that there is water vapor there, and water vapor also can exist only if it's cold and dense. So even in the surroundings of black holes, there's a lot of cold and dense gas, even already at a distance of 11 billion light years. And that means that the formation of black holes probably has to do with very cold gas clouds, and these black holes are probably also fed and become larger by attracting cold material. Okay, so the next part will be about synchrotron radiation. This is another way radio emission can be detected, and synchrotron emission in fact is what we see from the Milky Way, and synchrotron emission is what Jansky found almost 100 years ago in the Milky Way. Synchrotron emission is emitted by cosmic ray electrons, which are spiraling in a magnetic field, and in a single cosmic ray electron is producing emission, which is shown to the left. This is emission against frequency in linear and also in logarithmic scale, and each electron has a certain emission profile, and the maximum emission occurs at the frequency which is shown in the red formula. So the maximum frequency is 5 megahertz multiplied with the energy of the electron squared. If the electron is measured in GeV, and times the magnetic field in the sky plane. The perpendicular means it's in the sky plane, measured in microgauss. So if you have a few microgauss and a few GeV, then the frequency is in the range of several tenth or several hundred megahertz, which is the typical radio waves we observe with radio telescopes. But as you can see, if the electron moves very slowly, if the energy is not GeV but say MeV, then the frequency is dropping to very low frequencies which we cannot observe anymore, because, for instance, kilohertz radio waves will not arrive at the surface of the Earth, so we cannot see them anymore. So what we are seeing are very high energy cosmic rays, GeV ones, As you all know, the cosmic ray electrons have a rest mass of only 511 keV, so these are electrons which move highly relativistic, and these highly relativistic electrons, they can produce the radio waves we are observing. So this is why the observation of the Milky Way, which has been done by Jansky and many others later, this is again to remind you how the Milky Way looks in the optical, so full of stars. This is not what we see in radio. In the radio we see the cosmic rays and the magnetic fields in the Milky Way. So on this radio image of the sky we don't see any star. So we would see the sun if it would be there, but the sun has been subtracted from that image. This is a full sky view, so seen from the solar position. So we are looking in the middle towards the center of the galaxy, and so this is a whole. So we are sitting within the sphere, and that sphere is then cut out and just projected. That gives this strange coordinate system here. So this is the whole sky in the radio, and this is all full of magnetic field and synchrotron emission. And this is what Carl Jansky already discovered in the last century. The strongest radio emission comes from the center of the Milky Way, and the center of the Milky Way produces cosmic rays, and it's also full of magnetic fields. And this very nice image is now will be done much better with the Planck satellite, which is orbiting since a few years. And this is a first map of the Milky Way seen in radio emission seen by the Planck satellite. So why do we need a satellite here? The satellite is just is much better because it is not so much interference out there. So Planck satellite is at 7 million kilometers away from the Earth, so it will not suffer from all the disturbances we have to suffer from ground. So this is why this satellite is sent away from the sun. So the Milky Way center is seen in radio waves, and we can identify that as being in the Sagittarius region, and the brightest part here, the red part, is where the center of the Milky Way is located. I've mentioned that already yesterday in my talk. So there is another class of objects which are extremely bright in radio, and these are supernova explosions. And this is not unexpected because, as I mentioned, the cosmic rays are produced in supernova explosions, and cosmic rays emit radio waves, so it's no surprise that we can see them. Okay, right. So if somebody is leaving the conference, okay. So this is an example of a supernova explosion in the Magellanic Cloud in the year 1987. So the left image, the right hand is before and left is after the explosion. You see that a tiny star has exploded and becomes much brighter. And in the right part is a Hubble space image, how that happens. So this star exploded, it produces several rings, and these rings show how this the remainders of the stars is expanding into the universe. And now you do the same in the radio. We can apply this intercontinental very long baseline interferometry. We can detect a supernova. This is one observed in 1993 in the galaxy M81. And within 1 year, we can see how this explosion develops. And this is a diameter of much less than a light year. So with this very high resolution of only a few milli-arc seconds, which is thousandths of an arc second on sky, much better than any optical image can see that. We can already within 1 year see how this explosion develops. So this is extremely powerful to study the evolution of these explosions. But even more important is what is left over in the center of this explosion. And this is another success story of radio astronomy, because radio astronomers discovered that in the center of some of the supernova explosions, there's a remainder, there is a rest of the stars left over, and this leftover of the star is called a pulsar. A pulsar is a strongly varying signal, It's also pulsation is also seen in the optical. In the right image, you can see that the star in the bottom right side is switching on and off. But that has been discovered only after radio astronomers found the pulsar, and that has been done in 1968 by the PhD student Jocelyn Bell Burnell, and the supervisor was Professor Anthony Hewish, and that's with this very primitive telescope similar to Jansky's telescope, and they found that at certain positions on sky the emission is strongly fluctuating, and they called these pulsars. They were first worried that it may be extraterrestrial life which produces that, but then they found some theoretical models done by various people in Russia and the United States explaining that this could be the rest of a supernova explosions. So the supervisor got the Nobel Prize in '74. This is, I would say, a scandal for the Nobel Prize Committee, because the discovery was done by the student, but the student did not get the Nobel Prize. So I think this was not a good idea. So pulsars are magnetic lighthouses. So what is left over from this supernova explosion is a very small, tiny star of only 10-kilometer diameter. This star is not a normal star. It's like a big nucleus, atomic nucleus. It has a density of an atomic nucleus, but it's much, much larger. It's 10 kilometers. But within this 10 kilometers, a mass of similar to the solar mass is just concentrated. So density is extremely high, and it has also extremely strong magnetic field. And along the magnetic axis, radio emission is emitted. And if this beam hits the Earth or a telescope on Earth, then we see a radio pulse. This is called a pulsar, and this is observations done with the Effelsberg telescope of individual rotations of a pulsar. Doesn't matter which one is shown here. So each line is one rotation period of a pulsar, and you can see that there's not only a single pulse, there's a double pulse. The pulses have different heights. Sometimes they are missing. So it's not really a lighthouse. It is a very bad lighthouse. So any lighthouse would be closed if it has such bad signals. But a pulsar is not a very regular one. It is regular on average, but the individual pulses can be quite irregular. Anyway, this was a discovery of so-called neutron stars, and it showed that the theory of compression of matter into huge neutron stars and huge neutron nuclei was indeed correct. And there was even a second Nobel Prize for pulsars. You see, I'm also advertising radio astronomy because it was really successful in getting Nobel Prizes, because gravitational waves could also be detected for the first time with help of pulsars. If you have a double pulsar, so two pulsars rotating around each other, then the pulsars produce distortions in the gravitational field, and these distortions are periodic, and the periodic distortions cause the emission of gravitational waves. And these gravitational waves extract energy from the system, and that means the orbit of this system changes, and by the change of the orbital period you can compute how much you would expect from gravitational waves, and the result was exactly as expected. So this system loses energy exactly in the way predicted by general relativity by the emission of gravitational waves. So this was clearly worth the Nobel Prize. This time the Nobel Prize Committee learned their lesson, so they gave the Nobel Prize to the supervisor, Joseph Taylor, and to the student, Russell Holtz. Interestingly, the student is not working in astronomy anymore, but he was still, I think he was still happy to get the Nobel Prize in 1993. Okay, let's skip that. So, moving from radio supernovae and from pulsars now into extragalactic space, I can be very short here because I've explained some of these details already yesterday. So, as all galaxies have star formation. Also, these galaxies produce supernovae. Supernovae explosions produce cosmic rays. Cosmic rays emit radio emission, and this is why a radio image of a galaxy like Andromeda shows you where the star formation is taking place. And this is showing this very nice ring here I've already shown yesterday, which shows you where the supernova explosions happen and where also the magnetic field is located. And now a part which I had to skip yesterday because of lack of time, which is the radio galaxies. And these are very interesting for radio astronomers because radio galaxies show their nature only in the radio range, and in optical they are not, and they are completely unconspicuous. So radio galaxies are objects which are normally elliptical galaxies, quite small. So this is the radio galaxy called Centaurus A. Centaurus A means in the constellation of Centaurus, it is the brightest source. A is we call this A team. So the brightest radio source in each constellation gets the letter capital A. This is in Centaurus, and the galaxy shown in the insert in the upper left corner is quite a small object, only a few arc-minutes large. It's an elliptical galaxy, but in the radio range there are huge lobes, and you can see the degree scale. It is about 10 degrees on sky. It's a huge object on sky. 10 degrees is if you would put the full moon 20 times on top of each other. This is the scale, or the scale if you just stretch out your hand, it's the angular scale of the stretched out hand on sky. So it's a huge object, and this object is obviously powered by the small galaxy sitting in the middle, and this is called radio galaxy because the special energy is sitting in the radio range. So this is a combined image of the same object of Centaurus A. There's an optical image which is in white. There's a radio image which is the color is in green, and X-rays is in blue. And as I've explained yesterday, so the X-rays show the hot gas, the optical shows the stars, and the radio shows the magnetic field and the cosmic rays. And you can see that in the optical this looks like a more or less normal galaxy, but in the radio there's some outflow perpendicular to the plane of this galaxy, and there's also a halo of hot gas around that. So something is happening in the center of this galaxy, but unfortunately we don't have any insight into the very center. To do this, we have to increase our resolution. We have to use worldwide radio telescopes. And just to show you the most spectacular example of this kind is this galaxy, which is in this constellation of Cygnus, the Swan. This is the brightest radio source in that constellation. By the way, it is the brightest radio source at all on sky. It's almost as bright as the sun. The sun is only 8 light minutes away, and this galaxy has a distance of 500 million light years, and still we have the same power, radio power is arriving on Earth. But in optical, this is just looks like a normal star. This is, nobody would have realized that this is a very special object. Only if you move to radio waves, you then suddenly see what's going on. This small object is just a small dot in the middle. There are long channels of emission, and these huge radio lobes, which are to the left and right, they have distances of several 100,000 of light years. So energy is transferred along small channels and then released outside in the lobes here. And this is where the energy is going to. So we have a channel along jets and then lobes. So this distance is, as I said, about 500 million light years, and still this object has a size of several arc minutes on sky. So if you would have radio eyes, you would see this as lobes, even with a naked eye on sky, in spite of its enormous distance. And this transfer of energy is called a jet, and this jet is a supersonic stream of gas and magnetic field, and this needs to be transferred without energy losses, and this is a mystery how that will work. I will briefly come back to that in my last lecture on Thursday. So if we summarize these observations of Cygnus A in the brightest source in the constellation of Swan, the upper picture is the normal picture done with a VLA radio telescope, and then the magnifications are done with intercontinental interferometry, and you zoom into the very center, then you see the start of the jet. If you zoom even more, you can see that the jet is seen better and better, but still you do not see where the jet is coming from. And this very inner center, this is still not resolvable, even on a scale of a few light years, which we can resolve with this intercontinental observations. We still are not able to see where the energy is really coming from. And that means we need much better resolution. So in another case, in a so-called quasar, which is similar, it's related to radio galaxy, we can also, observing from year to year with intercontinental interferometry, we can see how the jet develops. We can see a small blob in the jet which is moving away from the central source. And if you compute the velocity of this, we know the distance, so we can measure the angle, so we can measure the velocity of this object, how fast it moves away. There's a surprise. This velocity is apparently more than the velocity of light. It is so-called superluminal motion, and that was a mystery for some time until it was discovered this is only an apparent superluminal motion, because this object is not moving to the right in the sky plane, but this object is moving towards us. And then there's a tricky effect. If an object moves with almost the velocity of light towards us, then you have the impression that it's superluminal. In fact, it is not, but still we learn from that this motion must be almost the speed of light. So these ejections from the centers of the quasars have to be powered enormously, and they have velocities which are extremely high and much higher than anything we have seen before in radio astronomy. So how can we explain this enormous energy input? And this can only be done, or only reasonably be done, with help of black holes. And so we believe that there's a black hole in the center of these quasars and radio galaxies, and these quasars, they attract a lot of matter. The matter can fall into the black hole, and some of the matter is then deflected along these jets, magnetic jets, and these jets are forming the lobes which are seen in radio astronomy. Okay, before I come to the next part of my talk, I give again a chance for questions. Any questions?
Yeah.
Why do you call radio galaxies galaxies? Are there stars?
We call them radio galaxies because they are galaxies made out of stars, but most of their energy is emitted in the radio range. This is a special class of galaxies. They are galaxies, but not normal galaxies. They are galaxies with a very bright and active nucleus. And this nucleus, the black hole in the nucleus, is what produces all the energy we see in the radio range.
Okay, thanks.
So, further questions?
No, I see.
Not the case, okay. Then I move on to the final part of my talk, which is about forthcoming radio telescopes. So, as usual, astronomers want higher sensitivity, higher resolution. if you argue with politicians, we argue the universe is expanding, and this we need larger telescopes. Don't take this serious, but maybe some politicians will be impressed by that argument. Okay, so how can we get a better resolution? So as I explained in the beginning, the resolution depends on wavelength and on the diameter of the telescope. So diameter is hard to change because the diameter for intercontinental interferometry is already reached. It's the diameter of the Earth. So you cannot do better. So if you want to have better resolution, you can only lower your wavelength. You can go from centimeter to millimeter wavelength. This indeed is a plan now. This is a plan to have a millimeter and sub-millimeter VLBI by connecting telescopes which can observe in millimeter, sub-millimeter, and these are telescopes in Europe, in the United States, in South America, and hopefully also soon in other parts of the world. And this is a system which will allow resolutions shown at the right edge of down to 16 micro arc second, so 16 millionths of an arc second. And micro arc second is the angular size of a coin which is lying on the moon. So just for your imagination. So if there would be a radiating coin, you would see it, and you could see the shape of the coin on the moon. Of course, coins are not emitting in the radio, so what we want to see, we want to look into the hearts of the quasars, and this is shown in this red picture on the right side. We would like to see the black hole. The black hole, of course, is black hole itself is black. We cannot see this, but a black hole is distorting space around it, and this distorted space can produce some artifacts which are shown here as a simulation. It would show some strange structures with a shadow in the middle, and this shadow, we call this shadow of a black hole. This is something we may be able to detect with this system of millimeter telescopes in future. And this is why this is called the event horizon telescope, because we would like to see the event horizon of a black hole. And if this is successful, then this idea that the quasars are powered by black holes will be confirmed. But I just said the size of a telescope is limited by the size of the Earth. But of course, that is not fully true. You could go to space. You could go because I'm speaking to a Russian community since last year, which was called Radioastronomy in the past. Now it's called Spectre R, between Russia and Germany, especially, is moving on a strongly elliptical orbit out to the distance of the moon, 350,000 kilometers. And that means the same resolution can be achieved as with the millimeter VLBI. The wavelength is much longer. We will be able to see get resolutions of about 10 micro arc seconds. So this is still in the test phase. So just today there's a big conference here in our institute with especially with strong contributions from Russia. So Russian people today in the institute to discuss how to use this instrument. It's only one satellite, and it's very difficult to collect sensitive data, but people are confident that within a few years it will also be possible to make images of the surroundings of black holes with this instrument. It's a long story. There were many delays, and I think we are very happy that this telescope is finally in orbit and it seems to operate. Telescopes we would like to have is telescopes at low frequencies. So telescopes are going to higher and higher frequencies, starting with Jansky at megahertz up to terahertz of the submillimeter telescopes. Now we have realized we should go back to the roots and then build telescopes at low frequencies. At low frequencies, as I've explained, the resolution is not very high. So to have good resolution, we need long baselines, and this is why a single telescope is not sufficient. We need a system of telescopes, and this is what is at the moment which is prepared in Europe, and this telescope is called LOFAR, the Low Frequency Array. This telescope operates between 10 megahertz and 240 megahertz, leaving out the FN band, where of course you cannot do any radio astronomy. At the moment, 33 stations are ready over Europe. Most of them, 33 stations are ready in the Netherlands, and plus 8 stations in other countries, European countries. So there are 5 stations in Germany, 1 station in France, in the UK, and in Sweden each. And there are plans for further stations in the UK, also in Ireland, in Latvia, in Ukraine, and also in Italy and in Poland. These are the question marks. These are stations which are planned. So this should become a European telescope. If Poland gets telescopes, then we should rediscuss whether there should also be further telescopes in Russia. It may be interesting to extend the baselines to the east. So LOFAR is a revolution in radio telescope design. It has a pure software telescope. It has no moving parts. It has no mirrors. It has very low costs, and it can do simultaneous multi-beaming. So the telescope can look at different directions at the same time because it's a software telescope. So this is the good news. The bad news this is a technological challenge because you need enormous computing power. You need very powerful data transfer. All the data have to be transferred online and produced online, and you have enormous data rates. That also means you have a need of very high data storage capacities. And this is why only now we can build this, because a few years ago this was impossible. Now we have the computers and also the data storage capacity to build such a telescope. So the difference to the classical telescope is shown in the next slide, which to the right. The classical mirror telescope is shown. If you want to change the direction on sky, you just move your telescope. The software telescope is just fixed antennas on the ground. If you want to change the direction on sky, you choose phase delay. So you take the connections between all the telescopes and then apply electronic delays, and the delays determine where you're looking at on sky. And the good thing is you can apply these delays several times simultaneously. That means you can depending on your computing power, do this several times. You can look at different positions on sky at the same time. In principle, you could look at all directions of the sky at the same time, but this is at the moment not possible with present telescopes. So the antennas of this telescope look really primitive. So the left is the so-called low band between 10 and 80 megahertz. It's just a system of 4 wires. So the stick in the middle is just a plastic stick to keep the wires straight. The wires, hopefully you can see them on the screen. These are 4 wires which are going to the corners. Then there is a plate which keeps away stray radiation and also grass from growing. And per station we need 96 of these stations. The cost of such an antenna in the foreground is less than 100 euros, and the parts can be all bought in the construction market. So this is extremely low-cost telescope. There's a small amplifier on top of that plastic pole. At the higher frequencies to the right, there's a styrofoam boxes, and then there are metal pieces, triangles put into these styrofoam boxes, hardly visible here. And this is not as cheap, but it's still extremely cheap. So such a telescope altogether costs less than 100,000 euros, but the computing power, this is a problem. This is where the costs are, so that drives up the costs of the whole station to about $500,000. But still, it is cheap. So this is why many small universities are able to participate, because the costs are really are very low, are much lower. Also, the maintenance costs are relatively low. So the center of this telescopes is in the Netherlands. The Netherlands have constructed it and have did the design. In the eastern Netherlands, they built an artificial hill, and you can see the different stations concentrated here. There are stations, the scattered stations of the low band, and this other station is the high band, covered with plastic. And then there's also a small ditch around that to keep the water off, because Netherlands has normally quite low. It's below the sea level. And then further out, there are further stations in the Netherlands, and then the outer stations. This is a picture of the station next to the Effelsberg 100-meter telescope, seen from the classical old 100-meter down to the new telescopes, another 2 times 100-meter telescopes. So in front there's the low band, and behind is the high band. You don't see the styrofoam anymore. These are covered by plastic to keep away animals and birds, and also the rain. And so this is operating well. It has been inaugurated last year by the Dutch Queen, and since last year it is already operating. This is another picture of another station which has been built in East Germany, in Thuringia. So this is a Schmidt telescope, optical telescope, which has been very active, and in fact the optical image of M31 was made with this telescope, but then they cut some hole into the forest and then built another LOFA station. This is an aerial view of that station. So that means even small institutes who have done only optical astronomy in the past, they can now participate in radio astronomy. That has been done altogether for 5 institutes within Germany, and hopefully more will come. So just explain again briefly how the image is done. Imaging is done for such a telescope. A single dipole antenna sees the whole sky, which is the gray area. But then if you combine all the antennas of one station, you can see into a certain direction, which is the yellow and the red area. And if you then combine various stations all over Europe, then you can have a very high resolution, which are the gray areas within the yellow and the red areas. So altogether, you get access to the whole sky with very high resolution. And this is, I will show you a few examples of that. So the next picture shows you what you can see with an individual station. This is a picture, an all-sky picture made with the Effelsberg station, made by one of our PhD students, Jana Köhler, and supervised by James Anderson. And so this is showing what a single station can do. The resolution at this frequency, it's around 150 megahertz. No, sorry, it is said there it's 62 megahertz. Is only about 20 degrees on sky, so it's a very coarse resolution. And what you see is a few A-team sources. It is Hercules A, Cassiopeia A, Cygnus A, from top to bottom, and then Sagittarius A, the Milky Way center, to the bottom. So this is not really spectacular. What is spectacular is the integration time. This has been done within 1.3 seconds integration. So you can get a picture of the whole sky within about a second. And unfortunately, the processing time is much longer, so you need a few hours to process that. So if in future we have faster computers, we will be able to monitor the radio sky on a time scale of seconds, and look for instance, for radio bursts. There's a speculation that there are bursting sources in the universe which would only burst for a millisecond or even less, or microsecond, and these normally are not recorded, but maybe with monitoring we will be able to see such sources with the stations. And if you then combine various stations, then you get really sharp images of objects. And this is one example made by one of our colleagues at MPI. This is the image of the Crab Nebula, which is a supernova remnant. In the middle, there's a pulsar seen in the Crab Nebula, and then there's a emission, which is the remainder of the supernova explosion, and also some ejector of the pulsar in the middle. And this has a resolution already of a few arcseconds at a frequency between 115 and 150 megahertz. So LOFAR is working fine. And another example from very new one of my students here at MPI, David Mulcahy. So this is a region in the northern sky of a diameter of 12 degrees. So this is the power of LOFAR. It can map large areas on sky, and each of this dot is a radio source. And each of that dot is probably a radio galaxy, because radio galaxies, as I've explained, are the brightest sources on sky. So if you make an image anywhere on sky, you will be full of radio galaxies. You would not see stars, you would not see normal galaxies, but you see mainly radio galaxies and quasars. But in the middle of that field, there is a normal galaxy. There is galaxy M51, which I've shown you already several times. So this is a magnification of M51. The beam size is not really good yet. It's only 1 arc minute, 60 arc seconds, but you can already see that indeed we see radio emission also from a normal galaxy. But this is the only normal galaxy in the field, and the reason is that this galaxy is quite nearby, and this is why we see it. All the other dots in that image are much more distant radio galaxies and quasars. And a final example of a LOFAR observation is a very nearby radio galaxy, the nearest radio galaxy beyond Centaurus A, so the second nearest galaxy on sky, which is Virgo A M82, which is a big elliptical galaxy in the middle, and the radio lobes are huge. They are of the size of about 100 kiloparsecs, which is 300,000 light years. And all this emission is magnetic fields and cosmic rays, and all has been produced in the center of that galaxy, of this monster galaxy in the center. So this is a colleague at Munich at MPA just recently published, so that also shows that LOFAR can see beyond the normal lobes and can see that this source is embedded in a cloud of charged particles and magnetic fields. So what else is planned with LOFAR? And so one of the aims of LOFAR is to look into the era where the first galaxies are formed. I've explained the cosmic microwave background, which occurred around 300,000 years after the Big Bang. But then there was a dark ages where we do not get any information. Only when the first galaxies were formed, which is about 500 million years after the Big Bang, then we have the possibility to see radio signals. And this is one of the aims of LOFAR, to look for these signals. And these signals should be appearing at the low frequencies. And of course, this is no chance. This is not by chance that these are the frequencies of LOFAR, because LOFAR has been built for that purpose. So if you observe at frequencies between 100 megahertz and 180 megahertz, you may see the hydrogen line, the line of the neutral hydrogen, redshifted. So the hydrogen line is normally at a frequency of 1412 megahertz, but if you're looking back in time, then this frequency is reduced by a factor of z plus 1, where z is the redshift. This is the expansion rate of the universe in the past, and at the redshifts expected for that time is around 10, and that means this frequency is shifted from 1.4 gigahertz to 140 megahertz, and that should in principle be observable with LOFAR. So the first observations have been started already, and so the colleagues, this is a group in Netherlands, Germany, and other countries, they hope that they can get some results already from in about 1 year from now. So, so this is about LOFAR, and just the last remarks before we have to come to an end is about the dream of all radio astronomers, which is a really ultimate telescope which will hopefully solve all our current problems and will give lots of PhD students a chance to write their PhD thesis, and will also create enormous amount of jobs. But this is a worldwide initiative. So a square kilometer array, a telescope which has a collecting area of a full square kilometer, is something which is that expensive that it can be only done by a worldwide collaboration. So the idea is to cover the whole frequency range accessible from the ground, from 70 megahertz, maybe even lower, up to at least 3000 megahertz or 3 gigahertz, hopefully higher, and that needs 3 different antenna designs. So the top left one is the low frequency, similar to LOFAR, and the bottom left one is the middle frequency, also development of LOFAR, and the bottom right one are classical dishes, but they have to be produced in many thousands of them, so the mass production is needed, and this is why these have to be built very light and very cheap. Again, we need several stations, we need several arrays to do this, and we need a good location. So where should we build such a telescope? And we should build it in an area where there is as little man-made interference, so it's TV stations and mobile phones and so on as possible. And this is a map of a military satellite done many decades ago about the interference situation on Earth. So as you can see, Middle Europe is very bad, so LOFAR is not the best place for a radio telescope. We will have to fight with a lot of interference. North America is quite bad, South America is not much better, China is not good, so Asia is not good, but there are only 2 regions where the interference situation is really acceptable for sensitive radio astronomy, which is South Africa and Australia. And in fact, these 2 sites were chosen as the site of this new radio telescope. And just to show you what the interference situation is, this is a frequency range between 100 megahertz and 1 gigahertz where the SKA should work. So the upper one is the interference situation in a large city, so there are no gaps, almost no chance for doing radio astronomy. The middle one, okay, we have to stop soon, I'm almost at the end. The middle one is in the small city, and the lowest one is the SKA site which has been chosen. So 2 sites have been chosen. Australia will be the low and high frequencies, and South Africa will be for the medium and high frequencies. So this has been decided just this year, and the construction should start soon. So 2016, there is a construction planned, and start of observations 2019, and then the phase 2, the full array, should be started to be constructed in 2020. So I have to skip the science to be done with this telescope. I'm sorry for that, and I just go to the last slide because we have some time for the discussion. And so this telescope will cost around €1 billion. That's worldwide. And not only money is needed, we need excellent people. So if people want to study radio astronomy, this is the ideal time. So please tell your students that radio astronomy has a brilliant future. We need good students, scientists, we need software engineers, and we need a lot of technicians to build up this radio telescope so that it will become a success in about 10 years from now. So that's the end of my talk, and thank you for your attention, and I think we have a few more minutes for final questions.
We haven't got questions?
We haven't.
So any more questions?
Maybe from Perm region, Likamsk.
Rainder, thank you very much. It was excellent presentation. Петя,
Thank you.
у тебя какие-то комментарии?
Нет, я не знаю, может быть, сегодня была бы чуть более техническая такая часть, да, поэтому, наверное, и реакция не столь активная в части вопросов. Но, как мне показалось, все было вполне понятно. Какую-нибудь реакцию дайте, пару комментариев, может быть.
Да, понятно. Меня тогда спрошу, вот это вот последний проект телескопа на громадной площади, а чем он отличается по возможностям от телескопа вот космического, который вот, ну, сейчас в 2011 году в России запущен? Там же гораздо больше база, чем, может быть, база в Австралии. Вот телескоп...
Вопрос в том, зачем нужны оба?
Да, чем этот будет лучше, чем тот, который уже создан, вот этот космический, с колоссальной базой?
Okay, so the question is concerned, what is the advantage of SKA in comparison with this space project, which seems to be much larger?
Yeah. So indeed, the space project has a much higher resolution. SKA has much higher sensitivity. So I did not have time to explain the aims of the SKA. The aims of the SKA are different. So the SKA wants to do a survey of the whole sky and detect practically all galaxies in the universe, more or less at the same time.
So
it's a
the
different...
main difference comes from the fact that in the space project you have only 2 points, yeah?
Yes.
And in the SKA it's a real array
It's an array
of stations which gives a very good space resolution, and the possibility to look for the whole sky.
The space resolution is not as good as the space telescope, but the collecting area is much larger. The space telescope has only 10 meters, and the SKA has 1 kilometer collecting area. So we can look much deeper into space, and we can also have much larger areas in the sky which we can observe them simultaneously. So this is the main advantage. And one of the main drivers of the SKA is to look for the origin of the dark energy, and this is needed to look back in time to measure the acceleration of the universe, then also to find several thousand pulsars in the Milky Way, and also this is one of the aims to look for signals of extraterrestrial intelligence. This is also one thing which is powering the SKA. So we really want to know whether there's any other intelligence in our Milky Way which is emitting, for instance, TV stations or airport radar. Or
this should be not the last argument when speaking with politicians.
No, this is of course is pushed forward for us as astronomers. We don't think this is very successful, but okay, politicians like this argument. Okay, any more questions?
Thank you.
Hello.
Нет, у нас вопросов нет здесь.
Тогда прощаемся до четверга.
Да.
Аудитория готова прийти снова?
Ну, мы физиков приведем первый курс, который будет со свежими силами.
Но там будет немножко новое. То есть речь пойдет именно о магнитных полях, уже такая очень конкретная физическая тематика будет.
Хорошо, спасибо.
Okay, then I thank everybody for attention and for your patience. And so if you like, we can see us again on Thursday. On Thursday there will be my third lecture about magnetic fields, and this is one of the big collaboration projects between our institute and Russia, between Moscow University and Perm University, and that will start on Thursday at the same time. Okay, then see you then.